So welcome to spectral graph theory. This is going to be a brief introduction to the theory of graphs which have some signal on them or something like that perhaps. But not just a graph, we're going to be looking at an undirected graph which has usually some kind of weights to describe how the vertices are connected by edges, and those edges will represent something. We'll get into that. But before we get too specific, let me just say some general questions which are guiding our study. So first of all, why study graph Laplacians? We want to think about what are some applications, reasons people care about that. Why is it called a graph Laplacian? I'll try to answer that here in this video in just a couple minutes. What can we say about the matrix properties of L? I'll get back to that in a future video. But I'll ruin, spoiler alert, L is symmetric and it's got some really nice properties. What can we say about the eigenvectors and eigenvalues of L? What do they mean? We'll almost get to that in this video. What does L reveal about the underlying graph? It's going to take us a few videos to get to that question. How does changing weights alter the graph Laplacian and or the theory? See, this is an interesting question because a lot of the literature assumes that the weight is just 1, whereas we're going to probably assign the weights values which correspond to some kind of physical notion or something on our graph. Before I forget, prerequisites, we do need to have some experience with graphs, not a lot, but we do need to have lots of experience with matrices and the theory of linear algebra to follow along in this talk. And then finally, one of our big questions is how does graph signal analysis fit into this discussion? I may or may not ever answer that in these videos, but that's certainly a question which is interesting. Now, let me just tell you some of the things that I've been looking at as I've been working on constructing these videos. First of all, the Wikipedia article on the Laplacian matrix is great. We'll be mostly borrowing from that in this video. Then we'll soon get to some articles by Fiedler, the Laplacian of graphs and algebraic connectivity, the algebraic connectivity of graphs. That's one's from 73, that one's from 89. Eigenvalues of the Laplacian of a graph by Anderson and Morley. Really nice little paper. A lot of beautiful calculations in there I'll share with you. And then the thing that probably is most powerfully guiding us long term is these lecture notes on spectral graph theory, which is a course offered by Yale University under the supervision of Daniel A. Spielman. And these notes are really great. I am fond of the 2009 ones, but he has other notes from the years between 2009 and the present. So there's probably a lot to learn there. I will not comprehensively cover everything, but probably lectures 1 through 6 I'll be touching on. And then finally, eventually, we'll get back to old and new results on algebraic connectivity of graphs, which is a pretty current review. Well, I guess it's 14 years old, but it's relatively new review by, I guess, at Brew. There's a more recent review by another author, Chinese, I forget the last name, but it's there's been, I think, a fair amount done since 2006 on this topic. So anyway, we're just trying to get to the start, so let's get to it. So first of all, before I get too theoretical, let's just look at an example of sorts. Well, it's not an example of sorts, it's an example. So, like I say, introduction and setup. Given a weighted graph, and I'm sorry if this is a review for some of you, but we'll go through it fast. You can watch it in double time if you want. Costs the same. Let's see here. So given a weighted graph, we may assign an adjacency matrix A. And so here's just a simple example. I got 5 nodes. Forgot my pointers. I guess I'll use this marker. I have 5 nodes, 1, 2, 3, 4, 5, and I've got edges, and I've written the weights 1, 4, 9, 16, and 25. I made them all squares because I'm going to take the square root of these numbers in a little bit, and I want to have whole numbers, all right? They don't have to be squares, obviously. That's just for my calculational convenience. So the adjacency matrix, the way it works, so like vertex 1 has a 1 in the 1, 3 because there's a weight 1 edge connecting 1 to 3, and it's got zeros elsewhere because node 1 is not connected to 2, 4, or 5. and we don't consider loops, so we're automatically going to have 0 down the diagonal for the adjacency matrix. Now, on the other hand, let's look at 3. 3 is connected to 1 with weight 1. 3 is connected to 2 with weight 4. 3 is connected to 4 with weight 9. 3 is connected to 5 with weight 25. All right? Now, this is a heuristic picture, right? It might actually be representing something in physical space where these nodes are, hundreds of miles apart, or they could be millimeters apart, or whatever. And these weights might might represent physical distance, but they might represent something more abstract, like number of common friends. Maybe these are social clubs, and these are the number of people that travel back and forth between the social clubs, or something. What's a social club? Anyway, I don't know. Something I guess people used to go to. All right. Now, so the definition of the graph Laplacian is related to this adjacency matrix. And at the moment, this is totally unmotivated. You're like, what? Why would this be the graph Laplacian? Why do we call it the graph Laplacian? I have not explained that, not even close. But here it is. L is D minus A, where D is a diagonal matrix formed from summing the columns of A. So for my example here, all right, if I scooch down here a bit, I guess I can, sorry, I don't want to give away too much yet. So here it is. Here's my D, which is formed from summing the diagonals of A, and then minus A, so that gives me this graph Laplacian, which is pretty typical. It's going to be symmetric. It's got negative entries on the off diagonal, and it has non-negative entries on the diagonal. We'll see in a later lecture that this forces the eigenvalues of L to be non-negative, but more on that later. Now, this is one of several popular choices for the graph Laplacian. There are others. There's one for random walks. There's another one that's called the normalized Laplacian that was studied in Chung's 2007 text on spectral graph theory. It's about 100 pages. But that's not too helpful for us here because we're going to be focused on the non-normalized or unnormalized, just plain graph Laplacian. All right. So another way we can look at constructing the graph Laplacian is pretty old. It is with what's called the edge or incidence matrix. This thing, let me cover this up here for just a second. The edge or incidence matrix goes back to Kirchhoff, I guess. So you got to think like an electrical engineer here. And so we have the same graph I had up above, all right, and the same weights, but now what I've done is I've labeled the edges 1, 2, 3, 4, and 5, and I've oriented them. This doesn't, just like when you do circuit analysis, that doesn't actually mean the current flows that way, or that way, or that way, or that way. It's just a mathematical convention to set something up. Same goes here. But with this incidence matrix, what we do is we put the nodes like this and the edges like that, and you get, and I figured out, I haven't found this in any of my references, but I'm pretty sure this works. If you have a weighted matrix, you can just take the square roots of the weights to inform the incidence matrix, as opposed to like most of the literature you'll find is for weight 1 stuff, so you wouldn't find an edge matrix like this probably in anything you looked at. Well, there's probably something out there somewhere, but I haven't found it. But anyway, here it is, -1, because when we look at node 1, edge 1 is leaving 1, puts that -1 here, and it's entering 3. So, hey. Oh, yeah, I can't read. So going down the column, exiting 1, entering 3. Edge 2, exiting 2, entering 3. See that? Edge 2, exiting 2, entering 3. Let's see, what does edge 3 do? It exits 4 and it enters 3. Exits 4, enters 3. How about edge 4? It exits 5 and enters 3. Exits 5, enters 3, right? Edge 5, it exits 4 and enters 5. Exits node 5. So there you go. That's the so-called edge or incidence matrix. Again, the orientation we choose, I guess there could be a problem where it's somehow given to you and has other physical interpretation. It's not really something we're doing here. I picked weights again so that the square root of weight was a whole number for my convenience. But you can check that when you multiply the edge matrix by its transpose, and by the way, a lot of the things I'm reading right now, they use a star for transpose because they're weird. Oh, I don't know. Anyway, maybe I'm the weird one, probably. Anyway, so if you multiply E times E transpose, you get back the graph Laplacian. And you can easily check this theorem here, this claim. For our example, it gives you back the same graph Laplacian. That's just a simple matrix multiplication there, like that. So I'll just leave that to look at for a second. In fact, I'll try to scan these and post these on my website so you can follow along in a PDF, but I haven't had a chance to do that just yet, but hopefully I will by the time I get these posted. So, all right. So this is neat because this means graph Laplacians have a direct connection to adjacency matrices, of which much is known. And also we can take any graph Laplacian and write it as the product of a matrix and the transpose of that matrix, where those matrices are the edge matrix is pretty simple kind of matrix. So that probably bodes well for the theory. The proof of this theorem in the weight 1 case is given in that paper by Anderson-Morley. It's about 2 lines long. If you want to look at it there, you can. All right. So why is it called the graph Laplacian? Well, let's look at that. Now, come on. Let's see here. So let me just derive a little bit of. Sorry if that was super loud. I'm talking close to the camera. So L is equal to d minus a, and I could rewrite that as the dii delta ij. Here delta ij is the Kronecker delta. It's 1 if I is equal to j. It's 0 if I is not equal to j. And the entries in the diagonal are given by the column sums. Right? The ith one is given by summing the ith column over all of its entries, so letting j range from 1 to n here. So that means that there's another formula we could write for the graph Laplacian, namely that it's given by the ijth entry of the graph Laplacian as a matrix, of course, is given by sum over k of a sub k I delta ij. So that is just kind of a sneaky way to write the graph Laplacian in terms of the components of the adjacency matrix. Now, this red comment here says, okay, well, also if the weights are all 1, then the degree of the vertex is the sum, is like basically the number of edges coming or going, and really that's, we're looking at undirected graphs, so I say coming and going, but I really shouldn't, just number of edges connected to a given vertex is the degree, and so we could write the graph Laplacian as the degree. Basically, it's a diagonal matrix of degrees minus the adjacency matrix. All right, so then, great. So you can think about the heat equation. Now let me try to, I don't know if this picture is too great, not really. So the idea here is, let me be more specific for just a second, and just, suppose we're thinking about node 1, right? And suppose it's connected to 2, 4, and 8. And you got a bunch of other, I'm not even drawing the other nodes, maybe they were here. 3, 4, 5, oh, I didn't want 4. 3, 5, 6, 7, all right? And for whatever reason, 1 is connected to 2 and 8, right? But these guys, they're connected amongst each other, but they're not, for whatever reason, connected to these. Or it could be that 7 is connected to 2. That'd be fine. The point is that none of these are directly connected to 1, all right? Then what Newton's law of cooling, you could think about Newton's law of cooling, which says what? Well, as I usually write it in differential equations class, it's something like dt dt is equal to something like k times T minus the room temperature. So what that says is that the change of temperature is proportional to the difference between the temperature of the object we're describing cooling and the ambient temperature R. So if you localize this idea, you could think about, well, maybe there's this graph and maybe these are things that are physically connected, and the only way heat can be transferred is by these edges, right? So in that case, you could talk about the change in temperature, which I'll use phi for here, just to be consistent with the Wikipedia article I'm stealing from. So d phi dt would be something like, k times, phi 4 minus phi 1, but it's, this is assuming that the edges are weight 1, basically. So something like this, plus k times phi 2 minus phi 1 plus k times phi 8 minus phi 1. So all these, when you have more things going on, you can look at the heat flow from each of the objects amongst each other. And so if you think about this, we can encode that kind of sum using the adjacency matrix, because the adjacency matrix in weight 1 case will just be 1 when I and j are neighbors, and it'll be 0 when they're not. So this sum over j of aij phi I minus phi j just does this kind of thing, but for an arbitrary ith vertex, right? So, and again, that's kind of naive in the sense that it's saying that the way the temperature flows amongst the different nodes connected by edges, it's the same. It's uniform throughout the graph, right? But that's just a starting point. Of course, you'd like to think about that becoming variable as you go on, right? Okay, so just going through the calculation then. Let me try to get this focused here. So as I was just trying to motivate why it's basically Newton's law of cooling applied to the graph. And so that breaks up into two sums, sum over j, sum over j. Phi I has no j dependence, you can pull that out front of the sum. Sum over j of aij, well, that's the sum across a row or column of the adjacency matrix, which is the degree of that row or column being summed over, in this case the ith one, so the degree of vi. And that's just writing along. And then, well, as I'd mentioned up here, this is, so I guess one more step, you really should change, well, fine, I keep the sum over j, I introduce a sum over j here. See, the point is that phi I, degree vi, is equal to the sum over j of Kronecker delta ij times this. It's a dirty trick. It's a little bit more clear on my next page of notes, so I'm going to wait to say more about it till there, but that's just a standard kind of trick calculation. And when you do that, then you've got this graph Laplacian ij entry summed over j, which is really, right, the matrix multiplication of that column vector with that matrix. And so there you go. Now, see, this may or may not make sense depending on how much differential equations you've taken, right? Or what your background is in physics. But this is the heat equation. Well, this is the heat equation over here. du dt is minus k nabla, the Laplacian acting on u. This says that the change in temperature is proportional to the spread of temperature in some sense. More on that in the next page here. So let me, again, I think we're mostly looking at graphs which have weights, so I'd like to go through this calculation not assuming weight 1. It's almost the same calculation, so why not do it right? What I just showed you was essentially in the Wikipedia article that I mentioned on graph the Laplacian matrix, I think. Okay, so here it is again. So same starting point, and then what I do, I break it into sums. sum over j. All right, and then paper's sticking to the table here for some reason. And then what I do is I rewrite this phi I as the sum over L of Kronecker delta Li phi L. This makes sense because this sum is 0 except in the case that L equals to I, in which case this collapses back just to phi I. So this is just a really kind of sneaky way to rewrite phi I, all right? And over here I'm just writing along. Then in this step here, something sneaky happens again. Notice one thing I do is I flip these guys, right? I change the order of the sum, which is a pretty standard step. You can do that for finite sums. If they're infinite sums, then you need some sort of like analysis argument there, but not here. And then here, I'm just relabeling. I switched the dummy variable of summation from j to L. All right, so that's just like relabeling the sum. That's not a big deal. But it helps you see where you're going because now we've got a sum over L, so I can pull the sum over L out like that. And then what I'm left with is the sum over j of aij Kronecker delta Li and then minus ail. And I've got this phi L I can factor out like so. Lo and behold, that is the graph Laplacian IL. And here I have not assumed weight 1, right? So, but you know, I think also this k could be set equal to 1 in this kind of discussion, and we could absorb that k into our definition of the weights in an application. So, because in a future lecture we'll be looking at eigenvalues of L and talking about how eigenvectors of L have to do with some sort of like solution to a discretization of this over some object which the Laplacian is modeling, let's say. Now just to, again, try to get back to the point of why is it the graph Laplacian? Well, it apparently is serving as a discretization of the Laplacian over a graph. Like if we think about a graph corresponding to some continuous object, maybe as a sort of numerical substitute for it, then you see that this matrix, the graph Laplacian, is appearing where the Laplace operator would have previously appeared. As we compare the heat equation in green to the heat equations in purple down here, this is the one-dimensional heat equation, the two-dimensional heat equation, the general heat equation. Again, it's correspondent, some proportionality constant to the Laplacian. And the Laplacian, again, is the divergence of the gradient. So in coordinates, it looks like that. In Cartesians, don't ask me what it looks like. In polars, it's not that. It's something uglier. In sphericals, it's even worse. But what this is describing mathematically is how this U is spreading out. So this goes to show you, anyway, that this graph Laplacian has some sort of matrix replacement for this operator in the context of the graph, perhaps approximating some continuous object or something like that. Now that's one viewpoint, right? But if you study these things before, you know there are other viewpoints. So hopefully we'll get back to those as well. But I think this is a good starting point. Also, I should mention that this Laplacian also, like the continuous Laplacian, also appears in the wave equation, like waves on a string, right? Waves on a membrane. So we shouldn't be surprised later when we see that the eigenvectors of the Laplacian correspond to some sort of discretization of eigensolutions to waves on a string or waves on a membrane. And we'll at least see the waves on the string one corresponding to the path graph, hopefully in a soon coming future talk. So I'm going to stop there for this one. Thanks, guys.